Hello and welcome to ACSC Academy. This is our very first video in the NIMSET series in which we will be dealing with the topic quadratic equation. This is a scoring topic from the algebra section and carries a good amount of weightage. It will be helpful to build the base for dealing with other chapters coming up. So let us gain a quick conceptual revision for this topic. What are the subtopics under it? Let us cover some theory about it, and then we shall move on to the problem solving session in which we'll be practicing a lot of problems until we gain some confidence in this topic. Keeping in mind that NIMSET is more about speed and accuracy rather than just knowing the concepts. So that's what we'll be focusing upon, and keeping all these in mind, let's get started. Let us begin with a quick review of what is a polynomial, what are the characteristics of it, and then we shall proceed slowly to the quadratic equations. Now, we know that a polynomial is any equation of the form f of x equal to an x raised to n plus a n minus 1 x raised to n minus 1 and so on until a naught x raised to 0. Now there are certain conditions that are to be satisfied for an equation to be called as a polynomial, and they are: there has to be a single variable. If I have an equation f of x comma y something as 3x minus 2y plus 4, then this does not qualify as a polynomial because it is a bivariate, or in that sense multivariate equation. So such equations are not said to be a polynomial. The next condition that we need to satisfy is that here the powers of x, which is being denoted by n, n minus 1 and so on, so that n, that has to be a non-negative integer. So here there are two different conditions. First, it has to be non-negative, which means 0 or greater than that, and next it has to be an integer. It cannot be irrational or irrational fractional form. All that is not allowed. So if we have an equation something like 3 by 2 x power 5 minus 4 by 7 x to the power 4 plus 3, then yes, this will be a polynomial because here we can see the powers are definitely positive, or we can say non-negative integers, 5, 4 and 0, that is allowed. Here the coefficients are rational numbers, and there is no restriction on what the coefficients can be. We can even have something like root 3 x raised to 2 x squared minus root 5x plus 2 equal to 0, that is also allowed. So that was the second condition. And lastly, we have that the leading term an, it cannot be 0. And if that is the case, if an becomes 0, then we will have to discard this first part and we will consider the equation from second term onwards. For example, if we have something as 0x cubed minus 3x plus 1, then this has to be written as simply minus 3x plus 1. And after doing that, this is what we call as the standard representation of a polynomial equation. And when it is arranged in this particular form, starting from the highest term, from the highest power of x, so on, going till x power 0, and if there are any missing terms, for example 3x raised to 7 minus 2x cubed plus 1. Now here we can see that many terms are missing. We just have x raised to 7, after that we have x cubed, and then x raised to 0. So if we had to convert this particular equation into its standard form, then what we'll be doing, we'll be appending the extra terms with their coefficients as 0. So that will be 3x raised to 7, 0x raised to 6, 0x raised to 5, 0x raised to 4, minus 2x cubed plus 0x square plus 0x plus 1. So that will be its standard form. And once we convert this into the standard form, then we can simply find out the terms. This one is a7, a6, a5, a4, a3, a2 and a1, a0. So those are the terms we can find out by comparing it with the standard equation. These ai are referred to as the coefficients of these terms. Now next thing we need to understand is about the degree of a polynomial. We already know that a degree is said to be the power of this highest term, the first term, an x raised to n. So this n is said to be the degree for that polynomial. And that's the reason why we discarded this an to be 0, because if that is the case, then I can add any number of zeros in front of it, 0x raised to 4, 5, 6, then that will keep increasing its degree. But that is not allowed. For this equation, its degree will simply be 1. And when a degree of a polynomial is 1, then we call it a linear equation. We already know that linear equation in one variable, then only that would be a polynomial. If the degree is 2, then we call it to be a quadratic equation. Similarly, when it is 3, that's called a cubic equation. For 4, it is a biquadratic equation, and so on. So the focus of this chapter will be upon degree 2 polynomials or the quadratic equations. Next, we will be dealing with the roots of a quadratic equation, the graphical representation, and we will be solving problems upon them. Let us understand about the roots of a polynomial. Considering the standard polynomial of this form, an x raised to n plus an minus 1 xn minus 1 and so on till a0 x raised to 0. First of all, we just learned about the degree of a equation. So based upon that, they can be classified into two types: even degree polynomial and odd degree polynomial. For each of them, there are some differences in the roots which we shall be quickly having a view upon. But before that, let us understand what exactly this root is. For that, we can have two different interpretations. First one can be, we can say that root is something at which the value of that polynomial becomes 0. F of x becomes 0 at that point. Then that point, that x, can be said to be the root of that equation. Similarly, the second interpretation can be made out from the graphical representation. There we say that root is any point at which that graph intersects the x-axis. Now here there are two roots, a0 and b0. So that is the abscissa of a point. We know that a point can be represented as abscissa and ordinate. So root is an abscissa of a point where the graph of that particular polynomial intersects the x-axis. And by intersect, we can also mean that it simply touches the x-axis. That is also allowed. So that is what we mean by a root. And now, depending upon the degree, if it is even or odd, we can have different types of graphical representations for the polynomials. Let us have a look on what are they. First, looking at the even degree polynomials, there are two cases in this. First one will be when the leading term, this an, that is positive. Now if that is positive, then the graph of such polynomials, such even degree polynomials, would always be lying above the x-axis. It can be like this. This one is having no roots because it is not intersecting the x-axis at any point. Or they can be like this: when it intersects it at exactly one point, then it has exactly one real root. Now we will be dealing with what is a real root and what is the imaginary root in just a moment. For now, let us understand what these graphs will look like. And similarly, if it is having multiple roots, then that can be like this. Here it is having two roots. So this is how these graphs will always be concave up, because the value of this leading term, the coefficient an, is positive. In the second case, if an was negative, then these graphs would be same. We would just be taking their inverse. They will be on the below. They will be below the x-axis, like this, or with one root, with two roots. That is how they will be. Similarly, coming to odd degree polynomials, we again have the same two classification. An is positive and an is negative. If this an is positive, then the graph of such polynomials will always be starting from below the x-axis and it will be going to above the x-axis. It may start from third quadrant or the fourth quadrant, that's fine. but it will always start below the x-axis and end above the x-axis. Similarly, if this an was negative, then that would start from above the x-axis and end below the x-axis. Now what does this imply? One thing we can notice in all of these four graphs is that all of them are intersecting the x-axis. This simply implies that all the odd degree polynomials have at least one root. They can have many, but one for sure. And what kind of roots we are talking about here? The real roots. For even degree polynomials, it is possible that there is no real root, such as this graph. It is not intersecting the axis at any point. But for odd degree, it is necessary for them to have at least one real root. Now let us come to this real and imaginary roots. If we have a polynomial of f of x of degree n, then how many roots will it have? It will have n roots. It will have exactly n roots, but some of those roots will be real and some of those roots will be imaginary. Both of them put together, it will have n roots. Now, when can we say that a root is real or not, and how can we represent them? As just we saw here, this was the xy plane. So the number of times these graphs intersect the x-axis, that will represent our real roots in the xy plane. We cannot represent imaginary roots in the xy plane. They will be complex numbers, imaginary numbers, and for that we will be needing the Argand plane. So they cannot be represented from these graphs. So that was what the interpretation of roots were. And if you find out at any point that an expression, let us say f of x, it is having more than n roots, where n is the degree of that particular equation. So if that is the case, that an equation of degree n is turning out to have more than n roots, then that will not be a polynomial equation, that will be an identity. What do we mean by identity? For example, you have something like 0x plus 0, that is your f of x. Now can you find out the root of this? Whatever value of x you put over here, it will always give the result as 0. So it has infinite roots. But by the definition, since its degree was 1, it is not even 1 because the coefficient is 0. You will say its degree is 0. So it should ideally have no roots at all. But it turns out that it has infinite roots just because we have retained this term. 0x term has been retained, so it is having infinite roots. Hence, this cannot be said to be a polynomial, it is simply an identity. So only an identity can have more than n roots, even by having degree n. So that was what about the roots were. Now let us move on to the quadratic equations and let us analyze what is the nature of their roots is and how can we find those roots. Now, moving on to quadratic equations, we already know some basic terminologies about them. There is a derivation behind them which we are not really concerned with because that is not relevant for solving the problems in this chapter. We'll be having a look at those derivations in the later chapters or while we are solving the differential equations and all those maximum minima thing. For now, let us have a quick review on what those terms are. And as we already know, we have a determinant d for a quadratic equation defined as b squared minus 4ac. Now what are these a, b and c? We already know the standard form of a polynomial y equal to ax squared plus bx plus c. So these a, b and c, they are the coefficients of the terms, or you can call them a2, a1 and a0 basically. We use the general terms a, b and c for them. So this particular thing, b square minus 4ac, that has been defined as a determinant of a quadratic equation. And what is the use of this determinant? It tells us what the nature of roots of that quadratic equation is. If it turns out that d is greater than 0, then we have real roots for that equation. And how many roots will it have? 2 roots. 2 real roots it will be having. If it turns out that d is equal to 0, then it will have real root, but there will be a repetitive root. Only one root will be appearing twice. For example, the graph of such a polynomial, such a quadratic equation will be, if its a is greater than 0, then it will be like this. It can lie on either side of the y-axis, but it will touch x-axis at exactly one point and it will be concave up. Whereas if a is less than 0, then it will be concave downwards like this. It will have exactly one root, one real root, and we would say that that's the repetitive root. Both the roots are the same. Similarly, for this case, when d is greater than 0, if a is positive, then its root will be like this. There will be two real roots. And if a is negative, then this way. Now it is possible that both the roots are positive, both are negative, or one is positive and one is negative. We will further analyze how to distinguish between these three cases. And now coming to the last one, when d is less than 0, in this case the roots will be imaginary. So they cannot really be represented in the real plane. For such a polynomial quadratic equation, the graphs would be like this. They will not intersect the x-axis at any point. So this is how D helps us identify the nature of these roots. And how can we actually find those roots now? We have known their nature, and we know that since it is a quadratic equation, it will have exactly two roots. Now it is possible that both of them are real. One is real, one is imaginary. Is that possible? No, it's not possible. Either it will have two real roots or simply one real root. In that case, it will be a repetitive root, or it will have both roots as imaginary because they always appear in pairs. So how will we be able to find those roots? For that, we have let us call those roots as a0 and b0, or you can use any pq or any representation, that does not matter. Or in general, we can say x. If it is a root of this equation, then that can be given as minus b plus or minus of root d by 2a. Now you already know this particular standard format in which we can find out the roots of any quadratic equation. There are two methods we have learned in school. First one was the factorization method, in which you can convert a polynomial equation into a product of two linear equations L1 and L2, and then you individually make them 0 and find out the roots. But it is not always possible for a quadratic equation to be factorized into two linear equations. So we use this standard technique, this formula method. You might have heard about it. This is the formula that is used for computation. First root is given as minus b plus of root d by 2a. Next root is given as minus b minus of root d by 2a. And both these roots are real, depending upon the value of d, of course. So that is how we give the roots of this quadratic equations. And now, depending upon these values of a, d, and the nature of roots, we can let us call the roots as alpha and beta, just for simplicity. Then depending upon the nature of these four terms, how will their graphical representations will look like? What will be the maximum possible value or the minimum possible value of a quadratic equation? That we all will be dealing with. Now, let us consider this particular case when the graph will look something like this. It is having two real roots. Hence, and since it is concave upwards, we will say a is greater than 0. It is having two real roots. And how do we analyze this? As we can see in this particular graph, this is the point of minima. Let us find the coordinates of this particular point. These will be the coordinates. We have to find those. The equation for this particular quadratic will be f of x equal to ax squared plus bx plus c. So now there are two different ways of finding the point of minima. If we go by the differentiation method, then let us see, it will be f dash x equal to 2ax plus b. And we will equate that to 0. From that we will be getting x equal to minus b by 2a, which means the x coordinate for this particular point or we can say this particular distance, that is nothing but minus b by 2a. And at this particular point, what will be the value of the function itself, which means f of minus b by 2a, that is what we want to find out. It will be a times of square of this thing, which means b squared by 4a squared plus b times of minus b, so that will be minus b squared upon 2a plus c. So now we will cancel out this one and we will be multiplying with 2 here and with 4a here. So this becomes b square minus 2b square plus 4ac. So it simply becomes minus b square plus 4ac upon 4a. And if we take minus out of this, then it is b square minus 4ac upon 4a. So we already know that d is, the determinant is given as b squared minus 4ac. Hence for this, the value of y, or the value of f of minus b by 2a, that becomes minus d by 4a, which means the y coordinate of this particular point is minus d by 4a. So from that, what can we understand? That such a quadratic equation will have its minimum value at minus b by 2a. This is the point where minima will occur. So that is the point of minima. And what is the actual minimum value that is achieved? That value is given as this y coordinate, the minimum value. So x coordinate gives the point of minima, and this y coordinate, or you can say abscissa and the ordinate, this gives the actual minimal value achieved by this function. And in the same way, if we simply reverse the sign of a and all the other things remain the same, then this will become something like this. The graph will look like this. For that, there will be a point of maxima. And what will be the coordinates of that point of maxima? Again, they will be given by the same coordinates, minus b by 2a, comma, minus d by 4a. So this particular coordinate gives us either the maxima or the minima of such quadratic equations, depending upon their a, if it is positive or negative. So this was the case we analyzed for the equations which were having two real roots. Now let us analyze for those which will have exactly one real root. Moving on to the case 3, let us also quickly find out what is the range of these two equations which we just saw. For this one, the coordinate was minus b by 2a, comma, minus d by 4a. And for the other one, this point was minus b by 2a, comma, minus d by 4a. What will be the range for these equations? This is the point of minima and it is going till infinity. So for this, the range will be minus d by 4a till infinity. Similarly, for this one, the range will be minus infinity because it is starting from the bottom, and it will go up to minus d by 4a. We can use closed interval over here because that is the value actually being achieved. And now moving on to the third case where d equal to 0. For both these cases, since there were two real roots, it was d greater than 0 case. Now we are moving to d equal to 0 case, which means there will be exactly one root. It can be like this if a is greater than 0, if a is less than 0. And also it is possible that the root is negative if it lies beyond the y-axis, or it can be like this. Similarly here it can be, root can be positive or negative depending upon if it is lying to the right or to the left of the y-axis. But for sure it will intersect the x-axis exactly once. Now for such equations the value of d is 0. So what the root will be? Minus b plus minus root d by 2a. But since d is 0, the root itself becomes minus b by 2a. There will be a single root whose coordinates will be given as minus b by 2a, comma. What will be the y coordinate for this? It is intersecting x-axis exactly once, so its y coordinate is definitely 0 everywhere. It is lying on the y-axis, on the x-axis itself, hence y coordinate will be 0. So this is what the root of such equations will be, minus b by 2a comma 0. Now if it belongs to the case 1, then its range will become minus b by 2a till infinity, and if it belongs to the case 2, then its range will become from 0 till minus b by 2a. Now is that the correct thing we just noted down over here? This one is x coordinate and this one is y coordinate, and for finding out the range, do we use x coordinate or the y coordinate? We use the y coordinate. So the actual ranges will be, for this one, the range, it is starting from infinity, so its upper limit will definitely be infinity. And what about the lower limit? It is starting from this particular point. We check the y coordinate and not the x coordinate. So since the y coordinate is 0, its range will be 0 till infinity. We often make this mistake. The correct range for this function is 0 till infinity. And similarly for this one, the range will be from minus infinity till 0, considering the y coordinate. So that is how we solved for the case when d was 0. Then coming to the case 3, when d is less than 0. In this case, we have no real root. So we cannot actually determine what will be the scenario over here. We simply know that the graphs will look something like this. They will not intersect the x-axis anywhere. And for such cases, we can still determine the maxima and the minima for these graphs. But the only thing is that when we actually get to compute their roots, then those will be imaginary. So we can write them as minus b plus minus iota root d by 2a. Then we can analyze them in this plane. What this iota will do, this is imaginary and we are multiplying them with this iota. So that will convert that into real, and then we'll be able to analyze them in the real plane. So for such equations, in this case 1 when a is greater than 0 and the case 2 when a is less than 0, here the point of minima, this point, that will be given as minus b by 2a comma minus d by 4 is simply as we saw in the case 1. It is possible only when we analyze them in this particular method. Similarly for the case 2, this is the point of maxima, that will be given as the same coordinates minus b by 2a comma minus d by 4a, and then in the similar fashion we can also compute their range. For doing this thing, what did we assume their roots to be? Both of their roots, alpha and beta, were assumed to be minus b plus minus iota times of root d by 2a, where d is the determinant and d is negative in this case. So root of d will result into a complex number. And we already know how to deal with complex numbers. This iota square, that becomes minus 1. Then this iota, this will also return an iota, and then that will convert into a real number. So that is how we will be dealing with it. So that was all about analysis of the roots. Now we can move on to know further details about it. What are the sum and product of those roots, and what are the type of questions we can expect from that. So here we are assuming the standard equation f of x equal to ax squared plus bx plus c, and we are assuming its roots to be alpha and beta. The determinant value will be same, b squared minus 4ac. So now if these alpha and beta are the two real roots of this particular quadratic equation, then without actually finding out the roots, we can directly say what will their sum and products will be. Their sum, which is alpha plus beta, that can be given as, there is a standard format which we have derived. It is minus b by a. These are the a, b and c, the coefficients. And in the same way, their products alpha, beta, that can be evaluated as C by A. So if you are asked, if you are given an equation and you are asked what will be the sum of the roots for this equation, it is not necessary for us to actually calculate the roots and then add them up to find what their sum is. We can simply check out the coefficients A, B and C and we can determine the sum and product of these roots. Now how was it actually found out? There is a simple derivation. If you want to have a look at, you can check out further. For this, what we actually do is we write this equation as A times of x minus alpha and x minus beta, assuming that alpha and beta are the roots, and this A is taken out common just to because its sign would matter. If it's positive or negative, that is taken as a constant outside. And when we actually compare both of these together, then we reach at the values of alpha and beta. For example, if we expand this further, this becomes x squared minus alpha plus beta x plus alpha beta. So we compare both of them together. This A coefficient of x square is the same. Their coefficient of x is b, and here it is minus of alpha plus beta, that too multiplied with a. So both of them have to be same, and from this we reach that alpha plus beta has to be minus b by a. And in the same way here, the constant term is a times alpha beta, and there the constant term is simply c. So from here we got alpha beta equal to c by a. So this is how we derive the sum and product of the quadratic equations, and they can be used for solving a lot of problems. Then there can be further manipulations that you have been given that if the roots of this equation is alpha beta, then find out the equation whose roots will be, you can be given as 1 by alpha 1 by beta, or you can be given as alpha beta and 1 by alpha beta, something like that. So simple sum and product can be used for doing all such manipulations, and it is easy to solve those questions. We will be quickly having some examples. Let us consider this particular equation. Let us say you have been given a quadratic equation x squared plus 7x plus 3 equal to 0, and it is said that its roots are alpha and beta, and you have to determine what will be the equation whose roots will be alpha plus 1 and beta plus 1. Simple. How will we proceed for this one? We will not be finding the actual values of alpha and beta, we will simply be taking their sum and product. Alpha plus beta, sum of roots will be minus 7 here because a is 1, and their product alpha beta will simply be 3. So now we have to find an equation whose roots are these. So the sum of those roots is alpha plus beta plus 2, which is, we already know alpha plus beta is minus 7. So this becomes minus 7 plus 2, that is minus 5. And the product is alpha plus 1 multiplied with beta plus 1. So that becomes alpha beta plus beta plus 1, which is, we already know alpha beta is 3, alpha plus beta is minus 7 and plus 1. So how much does this become? It becomes 3 minus 7 minus 4 plus 1, so minus 3. So we got the product of these roots as well. Now when we know the sum and product of the roots, we can find out the equation as x squared minus sum of roots into x plus product of roots equal to 0. That will be the equation. So we get x squared minus, what is the sum we got? Minus 5. So minus of minus 5 plus 5x, and plus product. What is the product? Minus 3. So this will be the quadratic equation whose roots will be alpha plus 1 and beta plus 1. In the same way, whatever different combinations of alpha and beta have been given, for example, you can try out this one. Given the same equation whose roots are alpha and beta, you have to come up with an equation whose roots will be alpha plus 1 upon alpha minus 1 and beta plus 1 upon beta minus 1. You have to solve for this one and you have to comment out what is the quadratic equation you are getting as a result for this.